In this video, I'm going to discuss some considerations about the strength of acids and bases. So the first thing I'm going to look at here are these thermodynamic measurements. And so this is using thermodynamics to sort of look at the strengths of acids. And so a lot of times you can't get this measurement very well, so we have to use Hess's law. So we can use these two equations here, so these two chemical equations here to uh, generate partial reactions and then put them together to generate the third reaction that we are interested in. So in this case, we're taking this second chemical reaction here and flipping it so that we get the negative of the enthalpy here. And so we will have our enthalpy and our entropy changes right here, so changes from reactants to products. So then we can use the definition of the Gibbs free energy, which is this equaling this. We rearrange it a bit so that we end up with this. So we can plot it as the natural log of our Ka versus 1 over T. And so the slope would be the negative enthalpy over R, and the y-intercept would be the negative entropy over R. So we can look at this for acetic acid. So we have our partial reactions here. So this one and this one. Then the full reaction that we're interested in is the deprotonation of acetic acid, which is this one down here. And so the following data could be obtained. So I got this data out of my inorganic chemistry textbook, which is the Meisler and Tarr third edition. And so this is the Ka, which are these numbers times 10 to the negative 5 plotted against the temperature here. And so we can use that to find the delta H, and the delta S for our reaction. And then that gives us some information about the strength of an acid, about what they kind of call the innate or intrinsic strength of the acid. So considering the strength of the acid, you know, they're trying to get at the strength of the acid independent of the solvent. And so just sort of the electron or proton rather affinity. And so that's kind of what we're looking at here as well. So in the gas phase proton affinity, they use a voltage of ionizing electron beam and a mixture of our base and H to so the voltage is sort of adjusted until we get this BH plus here, so this protonated base here. And so they're actually measuring the amount of this protonated base using mass spectrometry. So they look at the output from the spectrometer and find that they have this BH plus here. And so the enthalpy of formation of the BH plus can then be calculated from the voltage that was required to have this appear in the mass spectrometer, and the heats of formation for both the base and H plus in order to calculate the enthalpy change for the reaction. So the drawbacks for this, so this is in kind of a, a high energy environment. And so a lot of times the species are in excited states, and this can introduce some error to the actual measurements. And then so it doesn't account for solvent effects, but that's also sort of the point of this. And so we're trying to isolate factors other than solvent effects that are important to acid-base behavior. So if we look at the alkali metal hydroxides in water, these have the same basicity, so they're the same base strength. But when we use this, we actually find that that lithium is a weaker base than or lithium hydroxide is a weaker base than sodium hydroxide, which is a weaker base than potassium hydroxide, which is a weaker base than cesium hydroxide. And so we can actually see that the sort of innate or intrinsic basicity of these is different when we isolate it from the solvent conditions. Another thing to consider in our acid-base strengths are these inductive effects. And so this has to do with whether your base, for instance, has different things attached to it. And so whether those attached moieties are uh, sort of inducting, I guess, electron density into the base or taking it away from the base. And so we can look at this with two different examples here. So we have our nitrogen here, which can be substituted with these different alkyl moieties here, and we see that the nitrogen with 3 methyl groups, so that would be something that looks like this. So it has the 3 CH3s on it, CH3s, and those are electron contributing groups. So they're sort of pushing a little bit of charge onto the nitrogen, and so that makes the lone pair sort of have this larger lobe, and so that is going to be more basic than if you have, for instance, just the ammonia, which is the NH3. So if we have ammonia, which is NH3, for instance, the hydrogens the hydrogens are not contributing nearly as much extra electron density, and so this lone pair is going to be have a sort of smaller lobe on it there, and so that's going to be a weaker base than if we had these hydrocarbon or these alkyl moieties on it. And sort of in the opposite direction, if we have these electron withdrawing groups such as halides, that will have the opposite effect. And so if we look at, I guess I have phosphorus there, but we could think about it in terms of nitrogen as well. So if we have nitrogen with these fluorines on it, these are sort of removing electron density from the nitrogen. And so again, that's sort of making this a smaller lobe, and so that's going to weaken it as a base, which you can also think of in sort of the opposite direction. It would strengthen it as an acid. So if we had our hydrogen on here and we had our fluorines on here, this is sort of destabilizing this charged form of the nitrogen, and so this hydrogen here is going to be much more likely to leave this, and so that will make it more acidic. And so those are the inductive effects, and so that's another thing that affects the strength of acids. So then we can also consider the strengths of these oxyacids, which are acids that have oxygens bound to it, as the name would suggest. So the more non-hydrogenated oxygens, so that would be oxygens that look like this, uh, the more the electrons are pulled from the central atom, and the more partial positive the central atom, and the more it draws electron density from the OH, stabilizing the charged oxygen upon deprotonation. So, for instance, with this perchloric acid, if we lose this hydrogen here, the charge that we would end up with on this oxygen here is sort of pulled away from it, and so it stabilizes that negative charge on it. Whereas if we go down to the hypochloric acid, if we lose this hydrogen here, there is less stabilization of the charged oxygen on there, and so we see that we have this decreasing in acidity as we go from the perchloric acid to the chloric acid to the chlorous acid to the hypochloric acid. And then also for oxyacids, the more than one ionizable hydrogen on it, the pKa increases by about 5 for each H plus removed. And so remember, pKa, the higher it is, the less acidic something is. And so if we have our H3PO4 here that has a pKa of about 2.15, then when we remove one of those hydrogens, the next hydrogen has a pKa of about 7.2. Then after we remove that hydrogen, it goes up to about 12.37. Then same for this sulfuric acid. So this is less than 0, and we'll see why here in a minute, why we have to call this less than 0 rather than giving it like an actual strength here. But then that second hydrogen is pKa of 2. And so then we can also look at cation acidity. So remember, these cations are Lewis acids. And so we can look at the acidity of these Lewis acids. So a strong charge increases the acidity and causes one, lower pH in an aqueous solution, but also lower solubility of the metal hydroxides that result. And so if we remember from a previous video, so we have this Bronsted-Lowry sense of Lewis acids. And so we have the iron here in this case, which is solvated by these waters here. Then this water comes in and actually takes a hydrogen ion from one of those waters surrounding it. And so we end up with this FeH2O. It now has a 5 instead of this 6 here, and then this OH2 plus. And so this is the metal hydroxide here. And then so with iron 3 plus, you can actually have this happen again. And so we have this double hydroxide on here. And you could even go further and end up with a triple hydroxide. And so we see that as we sort of go down this list, we are getting less and less acidic. And so these three plus ions here are more acidic, so we see we have this low pKa. Then when we get to the 2 plus version, so this is the 2 plus iron here and the 3 plus iron here, the 3 plus is more acidic than the 2 plus. Then so we go on down the line here, getting less and less acidic. And then so the sort of, I guess, obverse effect to that is that these metal hydroxides then become less and less soluble. So we see we have the iron OH3 right here. And so this is 10 to the negative 38, which is extremely insoluble. And I actually have an image of the precipitate of that. But we see that these metal hydroxides can be varying in their insolubility. But of course, if we add acid to these solutions of these metal hydroxides, then the precipitate can disappear. So if we added, say, like H2SO4 or HCl to this iron hydroxide, we could protonate some of these hydroxide groups here, and that would sort of push this back in the other direction using Le Chatelier's principle. And so we could sort of end up back at our iron 3 plus hydrated by this water here. And so that would actually cause that precipitate to disappear. So another thing to consider for acid-base strength are the steric effects. And so if we have these more bulky subgroups on a molecule, that can actually block the formation of adducts. And so there are different kinds of steric effects. And so the first one that we can consider is sort of, I guess, the most obvious one, which is the F strain or front strain, where the bulky groups can make it more difficult for, say, the base to actually interact with the acid. So we see down here we have this base and then this Lewis acid here, and so when these try to bond like this, we see that this group right here is sort of clashing with the fluorines on our acid, and so we see that the affinity here, so this goes up, this is 128.1. This goes up a bit because we have this electron contributing group right here, sort of pushing charge onto the basic nitrogen right here. And so if you would expect, if you were just thinking about induction, if we had this right here, and so if you've taken organic chemistry, you know it's important that it be on this carbon instead of that carbon, but I won't get into that here. But you would think just through inductive arguments from induction here that this would make it even more basic than this, but in fact it gets less basic, and that's because of this steric clash here. Then there are the back strains, which so we have our base here and our Lewis acid here. Then when these interact, so if we have these R groups here, if these are bulky groups, they will sterically clash with each other sort of in the back right here, which is why this is called back strain or B strain. And so that will make this less likely to interact. Then we can also have internal strain or I strain. And so that is just when you form these adducts, you are sort of creating a species that have these lower or these higher energy sort of bond formations, or sort of bond angles and things like that that are less likely, and so those will make the base weaker in that instance. All right, so we also have the solvation of water, and so this is sort of how well something can really be dissolved in water. And so if we just think of induction effects again, so we have our nitrogen here with these three alkyl groups, and we would expect that to be the strongest base and then sort of going down the line here. But in water, this red one here is actually sort of switched into that position right there. And that's because in water, so if we have that right there, and then we have our three methyl groups here. So we have our three methyl groups here. This will be positively charged, but this there is less hydrogen bonding that can actually happen. With the water. So we are in water, and we want to form these hydrogen bonds here. But there's less hydrogen bonding that we can actually do to sort of stabilize this species. And so this is going to be a lot more likely to sort of get rid of this hydrogen here. And so we actually see that in general, we have this right here for any R group, that this triple substituted nitrogen here for the amine would actually be less basic than we would expect just from thinking about the induction effects that we discussed earlier. And so that is important when talking about acid and base strength, as well as the solvation in the solvent. So another thing that we have to think about is what's called the leveling effect, and that's the fact that in water, the hydronium cation is actually the strongest acid, and the hydroxide ion is the strongest possible base. That's because for any acid and for any base that we put in water, they're going to react with the water to form the hydronium and the hydroxide here. And so even though we say that like the hydroiodic acid and the hydrochloric acid, or the HI is a stronger acid than HCl. In water, they both just react to completion and form this hydronium ion. And so in water, if you add like equal amounts of hydrochloric acid and hydroiodic acid, uh, you are going to end up with just the same pH, because even though the HI is stronger than the HCl, they both essentially react to completion, and so we end up with just the same concentration of the H3O plus. So if you go to weaker acids, so if you compare like HCl to acetic acid, this is not the case. If you add like the same concentration of HCl and the same as your acetic acid, the HCl reacts to completion, and so that will be a lower pH than the acetic acid. And so, yeah, when the concentrations of these are the same, you'll just get the same pH. So when you get to extremely high concentrations, there could be a small difference, but the pH of water is essentially limited and must fall between pH of 0 and 14, which is why I was saying earlier up here why this has to be said just to be less than 0 rather than putting like an actual number on it. But this is also true of other solvents as well, that the pH is limited by the ability of the solvent to donate or accept H plus ions. And so, for instance, if you have a solution where the solvent is acetic acid, so glacial acetic acid, then this acetate here will actually be the strongest possible base that you could have in it, because if you put a stronger base into it, it'll just react to completion until you end up with this right here. So a concentration of this equaling the concentration of whatever base you put into it. So only a very strong acid could force H plus onto the acetic acid, where we end up with this right here. And so inert solvents, such as hydrocarbon solvents, have little to no acid-base properties for themselves, and so they allow for a very wide range of acid-base behavior of the solutes that you put into it. And so this is just looking at some different ranges of pH for different solvents. So we see our water here, which goes from 0 to about 14 right here. And so that is the range of water. But if we have these other solvents here, we see that we can have different pH ranges. And so this figure right here, I mostly wanted to put, because if we have like these hydrocarbon solvents here, we see these very wide ranges of pH on here. So we see up here water has a range of 14, but then when we get to like these hydrocarbons, we see that the pH range is things like 86 and 120, and so the ranges of pH can be quite high for those solvents. The other thing I wanted to from this figure is to introduce this idea of superacids, and so anything to the left of that dotted line there is considered a superacid. And so a superacid is essentially anything that is more acidic than sulfuric acid right here. And so, yeah, like I said, more acidic than sulfuric acid. So we use the solvent-independent Hammett acidity function, which is this, and then these species here in the logarithm are usually this weak aniline base, so which has aniline has a pKb of 9.38, but they often put electron withdrawing groups on it to make it an even weaker base. And so why they would want this weak base is you want to look at an acid that is, extremely strong. So you want an acid that can essentially force H plus ions onto this base. So you want something that can sort of force these H pluses onto the base. And so you want a very weak base that's not going to accept those H pluses, and so this a very strong acid is something that would be able to get deprotonated by something that's a very weak base. And so that's how you can sort of measure the strength of these superacids. They are things that can actually protonate a very weak base, like an aniline, or especially an electron withdrawing group substituted aniline. And so that will help you to make this calculation about the strength of these superacids. So the more negative this H sub naught here, the stronger an acid. And so we have our sort of reference here, this sulfuric acid, which has an H sub naught which hovers around -12. And so we see then here that we have all these superacids here. So these are acids that are even stronger than the H2SO4. And so these superacids can be used in various things as catalysts. For instance, in organic chemistry, the Friedel-Crafts reaction, which you can see the Wikipedia for that here. And so this, for instance, is using this AlCl3, which with Lewis acids is sort of taken as the standard, similar to our H2SO4 here. And so anything that is more acidic than this AlCl3 can be considered sort of a super Lewis acid, I guess you could say. But anyway, those are sort of various considerations for the strengths of acids and bases. And so, it's not always as straightforward as you might learn in like a general chemistry class, just about like the pKa and pKh. So, there are this thing about the sort of intrinsic or innate strength of the acids and bases, which you can find with these thermodynamic measurements and these gas phase proton affinity measurements. But then we also have to take the inductive effects into account. With these oxyacids, you have to take the sort of oxygen content into account, but also the H plus content for oxyacids with more than one ionizable hydrogen. Then with cations, so with Lewis acids, you have to take in the charge into account for it. Then of course we have to take steric effects into account, because even if you have something that might be sort of an innately strong base, for instance, you might have these steric effects that actually reduce the strength of the base. And then also the solvation in water. So for instance, with our amine groups here, our substituted amine groups here, the more they can interact with the water, the stronger they'll be. So these induction effects considerations aren't the only thing that we can take into consideration here. Then there is the leveling effect, which is just saying that the solvent that you put your acid into is going to sort of affect, essentially the ultimate strength of the acid, where the different solvents can have different pH ranges, and so they can have different acid strengths just based on what solvent it is actually dissolved into. And then using that, we can actually find these superacids, which in different solvents can become even stronger acids than what you would find in water. But anyway, I hope you found this video helpful. As usual, if you want to look at my lecture notes in a little more detail, those will be linked to in the description down below. But anyway, I will see you in the next video.